Greetings everyone and welcome to the first episode of Astronomy Insiders. The topic of the lecture is quantum gravity and the atoms of space-time matter. Our speaker is Honorable Mr. Tejinder Singh, who is a professor at Tata Institute of Fundamental Research, Mumbai. Link to the document, our Discord server and resources related to the lecture are provided in the description box, so don't forget to check it out.
So these are the three things we will talk about today. The force of gravitation, the laws of quantum mechanics, and how to put these together is the problem of quantum gravity, and that will lead to this new concept of atoms of space-time matter. The force of gravitation, I think everybody is familiar with. Newton first gave us the three laws of motion of bodies. We know the most important one is the second law of motion, that the force applied on a body is equal to the mass of the body multiplied by its acceleration. We just briefly call it F equals ma. Now, a particular example of the force, as you know, is the force of gravity. It makes things fall to the earth, and it also makes planets go around the sun. This is the law of gravitation. So if this particular force I want to know, what is the force of attraction between two gravitating bodies? It is given by this law, Newton's law of gravitation. What is the force with which the sun pulls the earth? The force is proportional to the mass of the sun, is proportional to the mass of the earth, and it falls inversely as the square of the distance between the sun and the earth, or any two bodies. And V is the constant of proportionality, which is measuring the strength of the gravitational attraction, called Newton's gravitational constant, Newton's constant of gravity. So this is about all we need to know about the law of gravitation, as it is applicable to large objects, like the objects around us in this planet or in this room, or between planets, sun and the planet, stars. Okay. What did Einstein do to Newton's law of gravitation? Newton and Galileo were aware of this very interesting and important fact, which is the following. So let us look at this relation. This is the force of attraction between two bodies, say sun and earth, and how much acceleration it will produce on the earth. To find that out, I must use second law of motion, F equals ma. This is the force of gravitational attraction equal to mass of the earth times the acceleration felt for the earth. Now you notice, because the force depends proportionally to the mass of the earth's mass cancels out in this equation, meaning that the acceleration of the pulled body is independent of its mass. The acceleration of the earth only depends on the mass of the sun. This of course is very remarkable. It means that acceleration due to gravity is independent of the mass of the object being moved. Like from the top of a tower, Galileo did this famous experiment to drop a rock and a feather. Both will reach the ground at the same time if there was no air resistance, which is the same thing as saying that the acceleration is independent of this mass. In a gravitational field, heavier bodies fall as fast as lighter bodies. Einstein put this to some good use. He's concluded and proved that if the acceleration is independent of the mass of the body being pulled, then gravitation can be thought of as not a force but the curving of space-time. So here is the sun, here let us say the earth going around the sun, This picture is trying to show us that space and time around the sun are no longer flat. They have picked up a curvature, and the response is that the earth, instead of going in a straight line as it would have done if there was no curving, is taking this new path which is a result of the curving of space-time because of the mass of the sun. So Einstein concludes that the, there is no such thing really as the gravitational force. Instead, there is curving of space, time, or of space as produced by material bodies like the sun. And of course, the earth also curves space time. Everything that has matter, mass, and energy curves space, and gravitation can be thought of as the curvature of space time. So Newton gave us laws of gravitation. Einstein generalized them to a more general situation, which is valid even closer to speed of light, and he showed that gravity can be thought of as the curvature of space. This is all we need to know about gravity for the moment. Now, unlike Newton's law of motion, small objects like elementary particles like atoms, elementary particles of which atoms are made, electrons, protons, neutrons, quarks, they do not obey Newton's laws of motion as it was any. The laws of motion obeyed by elementary particles or small objects on atomic scales are different. They are the laws of quantum mechanics. What is relevant for us is the following. In particular, an elementary particle can be at more than one place at a given time, which is what we mean when we say it behaves like a wave. So, wave is spread out in space, it's not at any particular location. An elementary particle like an electron also behaves like a wave and is spread out in space. That is the aspect of the laws of quantum mechanics that we will need for this talk. We say that quantum systems obey the principle of superposition. If it is at place 1 and if it is at place 2, it can also be at both places at the same time. So remember this important difference between the Newton's laws of motion and the laws of quantum mechanics. Newton's laws apply to large objects, called classical objects. They move along a definite path. They do not spread around like a wave, whereas atomic systems are smaller, they spread around like waves. And that's the difference between Newton's laws of motion and the laws of quantum mechanics. So I am going to ask a question which will lead us to quantum gravity. But before we get there, let us recall for ourselves what are the different kinds of elementary particles which obey the laws of quantum mechanics. You will see why I bring this up. So what is there inside the atom? There are protons which are charged plus E, where E is the charge equal to the electron. Neutron is electrically neutral, it has charge 0. Electron has charge minus E, negatively charged. Proton and electron have opposite charge. The electron is an elementary particle. As of today, we do not think it is made up of something. It is by itself. This electron is an elementary particle. By that criterion, protons and neutrons are not elementary particles. Protons and neutrons are made up of quarks. They have include a down quark and an up quark, is what protons and neutrons are made up of. Down quarks have an electric charge of minus E by 3, minus 1/3 the charge, 1/3 the charge of the electron. Up quark is positively charged it has a charge two-thirds that of the electron but opposite sign. A proton is made up of two up quarks and one down quark. Let's check. Two up quarks is 4 by 3 and minus 1 by 3, that is plus equals E. That's correct. A neutron is made up of one up quark and two down quarks. Let's just check. 2e by 3 minus 2 this is 0, so neutron is 0. So remember, what are our elementary particles? Down quark, up quark, electron, and something known as the neutrino. It does not bind anything, but it is responsible for what is known as beta decay, the heat force, conversion of a neutron into a proton and an electron and an antineutrino. So a down quark has an electric charge minus 1 up quark has electric charge 2 e by 3, the electron minus 3 and the neutrino 0. So all the matter that we see around us inside atoms is made up of these elementary particles, quarks, electrons, neutrons. But you may have heard that for every particle there is also an antiparticle which has the opposite charge. For neutrino, it is something known as the antineutrino. For the down quark, which has a charge minus E by 3, the antiparticle is anti-down quark E by 3. This is antimatter. On the right hand side is antimatter. It has the electric charge opposite that of matter. So up quark is 2 E by 3, anti-up quark is minus 2 at E by 3. Electron is minus E, positron is E. Note that the universe has more matter than antimatter. Why? We don't know. It's an unsolved problem. The antiparticle has the same mass as the corresponding particle. The sign of the electric charge changes, but the mass remains the same. And now we could also ask a very important question. You notice charge is coming only in these four values. If E is the charge of the electron, absolute magnetism, the only allowed values are 0, 1/3, 2/3 and 1. You could ask why. Why is that so? Why can't it be half, 1/4, 3/4? Why these fractions only? Why is electric charge quantized and why is it quantized only in these units? Let's remember this question. There is some more knowledge we should have about elementary particles. They come in 3 generations, each one. What does that mean? The electron has a heavier particle, we call it as a father in family. It's a daughter, mother, grandmother, if you want to visualize. They all have the same value of the electric charge, but they differ in mass. That's a 3 families, 3 generations in a family. Electron, muon, tau. Same for down quark. Down quark, straight quark, bottom quark, minus E by 3. And again, everything has a corresponding antiparticle. Up quark, charm quark, top quark, 2 E by 3 differing only in mass. Electron neutrino, muon neutrino, tau neutrino, the charge is 0. But we don't know their mass. Neutrino mass is we know they have mass, but we don't know how much or why. So what is changing in the 3 generations is the mass. So remember, elementary particles come in 3 generations which differ only in mass. So here I give you an example, the mass values for these particles. Suppose the electron you set as 1 unit, whatever is the mass, you call it 1, and these are the ratios. The muon is some 200 times heavier than the electron. The tau electron is 3000 times heavier than the electron. The down quark is 9 times heavier, about. The up quark is 4 times heavier. Neutrinos, some idea we have. So these are mass ratios. If the electron is 1, the top quark is 340,000 times heavier than the electron. Notice, these numbers are so strange. Why has nature chosen these numbers? The mass is quantized, just as the electric charge is quantized. But electric charge, at least you could see the ratios are simple: 0, 1/3, 2/3, 1. But what about the ratios here? Here it's okay: 1, 9, 4, 1 and 2 square and 3 square. What's going on here? You see? These are very strange mass ratios, and you will see why I bring this point up. Today we will also explain what is the origin of these ratios. And finally, we know that there are 4 different kinds of fundamental forces. The gravitational force which acts between all particles. Everything attracts each other gravitationally. Same way, the weak force is there between all particles. The electromagnetic force is only there between charged particles, and only quarks experience what is known as the strong force or the nuclear force, which binds quarks into protons and neutrons inside the atomic nucleus. Okay, so that was a very quick introduction to elementary particles. There is charge quantization, there is mass quantization, and there are 4 different kinds of forces. But we don't understand why charge and mass are quantized in this particular way. But by the end of this talk, we will have an answer. Okay, so we are already now up to the third and main part of the talk. I told you about Newton's law of gravitation and Einstein's law of gravitation, namely curving of space-time. Then I told you about the laws of quantum mechanics, namely that an elementary particle, unlike the large objects, an elementary particle can be in more than one place at the same time. Okay, and right. So that brings us to the central question of today's talk. I introduced the subject quantum gravity and the atoms of space-time matter. So what's the question? If an elementary particle can be at more than one place at a time, what is the gravitational field it produces? I hope you appreciate this question. The sun produces a gravitational field given by Gm by r squared, where m is its mass and r is the distance from the sun. But suppose you have an electron which is spread out in this entire room like a wave, and you ask this question, what is its gravitational field? You might say, okay, I will apply Newton's law of gravity. But suppose you choose a point in space and you ask how far away is that point from the electron. This question is meaningless because the electron is spread out around like a wave. So the electron is also there at the left of the room, it is also there at the right of the room. It doesn't have any fixed position like the sun. One elementary particle is everywhere. So how am I to find out what is the gravitational field produced by an electron or by a quark? I cannot apply Newton's law of gravitation to it. That is very clear. So we are asking, in what way does an elementary particle like an electron curve space-time? This is the problem of quantum gravity. So gravity, because we want to find the gravitational effect, which is same as curving of space-time, and quantum because the particle obeys the rules of quantum mechanics, which is wavy. So, what is quantum gravity? Quantum gravity is the question: how do elementary particles like quarks, electrons, and neutrinos, how do they curve space-time? What is their gravitational field? This is the question of quantum gravity. Now we come to the next new concept, that if the particle is at all places in space and all places in time, and if the particle is also curving the space-time, there is no meaning to saying that the particle and space are different from each other. The particle is all over space, it is also curving space. So how will I tell which is the particle and which is the space? There is no distinction. So we introduce a new concept, space-time matter, which I will make more precise as we go on. And say universe in quantum gravity is made up of atoms. Atoms not all like ordinary atoms like carbon atom or oxygen atom. Atom means a unit of structure. They say in quantum gravity, space-time matter is one concept. Space-time is no longer separate from matter, and universe is made up of these atoms of space-time matter. And now I will give you the mathematical picture. It's quite simple. Behind how do we describe atoms of space-time matter, that will give us a precise answer to this question: what is the gravitational field produced by quantum mechanical particles like electrons and quarks? Okay, so it turns out that when we will correctly describe the gravitational field of elementary particles, we will also find the answers to these questions. Why the electric charge has this particular ratio, why the masses have this strange ratio that I showed you, and why are there four different kinds of fundamental forces. These questions get answered when we find the correct way of describing gravity of elementary particles. And to get there, I am going to use numbers known as the Octonions. Big sounding name for a simple thing. I will first introduce what are Octonions, and I will then explain what do they have to do with atoms of space-time matter and quantum gravity. Okay, let's talk a little bit about numbers. We'll do a little bit of elementary mathematics and arithmetic. Suppose we are familiar with numbers, natural numbers, real numbers, rational and irrational numbers. So I'm going to generalize the concept of numbers. Let us ask this question: which are the kinds of numbers in which we can add them, subtract them from each other, multiply them, and divide one from the other? Addition, subtraction, division, multiplication. Numbers which have these four properties are called division algebra. The division is the most important, most subtle of these operations. So we are asking, so there is a theorem in mathematics that there are only four different kind of numbers in which all these operations are possible. There are only four different kinds of division algebras. Octonions are one of them, so we will get there slowly. Let me explain to you which one are the others. Okay. The simplest and most familiar division algebra is that of real numbers. You have a picture, real numbers, you know what a real line is. So these are special kinds of real numbers. Natural numbers, integers include negative numbers, rational numbers, which are the fractions, irrational numbers like square roots, or include pi, or the exponential natural logarithm e, those are transcendental numbers. All these together, rationals and irrationals and everything together, are what we are most familiar with. These are real numbers. This is the first kind of familiar division algebra. I can add, subtract, multiply, divide. But this is not all. This is then comes what comes next, complex numbers. This also you are probably familiar with. What is the origin of the idea of a complex number? Which is the number whose square is minus 1. We don't know anything which has a negative square. So if you take 3 into 3, it's 9. Minus 3 into minus 3 is also 9. The square of a negative number is also always positive. But still, mathematicians are puzzled. Can you define something whose square is minus 1? They said, okay, we don't have a feel for it, but we can just make a symbol. New concepts are born from symbols. If there is some number whose square is minus 1, it means that the square root of minus 1 is that number, right? Let us just denote it by the symbol I and do nothing. Just denote it by the symbol I and call it, I stands for square root of minus 1, so that I square is minus 1. If you are familiar with iota or the imaginary unit. Now, you can make what are called complex numbers, a plus ib, where a and b are real numbers and I is square root of minus 1. I'll always carry it around. Turns out these are very powerful numbers. They play a very important role in physics and mathematics. So 3 plus 8i, for example, is a complex number made up of two real numbers and the imaginary unit. What are the applications? The rotation of a vector in a plane can be understood through complex numbers. A vector can be expressed as a complex number. How? So here is a two-dimensional plane where I have drawn the x-axis and the y-axis, and here is a vector A which has x component a1 and the y component a2. So the vector has a1, a2 as its component. I can also label this by the real and imaginary parts of a complex. I forgot to tell you, the coefficient of iota is called the imaginary part of the complex. So a plus IB, a is the real part, b is the imaginary. So let us write the components of this vector, and hence the vector A itself. You can put an arrow on top of it to denote a vector. A vector is A1 plus A2 times I. The real part of the complex number is the x component. So you move A1 in this direction, and you move A2 in the vertical direction. So imaginary component of the complex number is the y-axis. So you can either think of it as a two-dimensional plane made of two real directions, or you can equivalently think of it as what is known as the complex plane. A1 plus A2i, the real horizontal direction is the real part of the complex plane. The vertical direction is the imaginary part of the complex. So a vector in two dimensions can clearly also be represented as a complex number, and the good use is, if you want to know what happens to a vector when you rotate it in this plane, you can use complex numbers in a very simple. So suppose I want to rotate this vector by 30 degree anti-clockwise or clockwise. This is I should say anti-clockwise here. You want to change, rotate this by 30 degrees in this plane, and you want to know how the components change. Here is the simple result. Take the original vector a1 plus a2I multiplied by cos 30 plus iota sin 30, and this is your new vector. The resulting vector will have components obtained by multiplying this complex number by the complex number made from the vector. And we know how to multiply two complex numbers. It is very straightforward because it is a division algebra. So rotations in two dimensions can be described by acting vectors by suitable complex numbers. So you can write a vector like a complex number multiplied by this complex number made from the angle, and you will get the new vector whose components are given. Okay. So complex numbers, which are the second kind of division algebra, real numbers, complex numbers, and these explain to us how to rotate vectors in two dimensions. But we know that our space is three-dimensional. X, Y, Z. I can have one more axis. Are there any numbers which can describe rotation in three dimensions by this kind of a trick? Complex numbers for rotation in two dimensions. What about three dimensions? This was a famous discovery Irish mathematician Rowan Hamilton made in 1800, 1840 something. He discovered this third division algebra, the number system known as the quaternions, which he showed could describe rotation in three dimensions. So a complex number has two components. A quaternion has four components. And an octonion will have 8 components. We'll get to the octonion. These are the only 4 division algebras: real numbers, complex numbers, quaternions, and octonions. Anything after that, the division doesn't remain possible. You cannot divide numbers by one by the other after octonion. That's the beauty of this number system. There are only 4 kinds of them. So what is a quaternion? A quaternion Q is made from 4 real numbers. A complex was made from 2. This is made from 4. A0, A1, A2, A3. What are I, J, and K? I, J, and K are also imaginary units. Each one of them has a square minus 1. I square is minus 1, J square is minus 1, K square is minus 1. So they are like iota, but they are not equal to each other. I square and J square and K square are equal, but I and J and K are not equal. On the other hand, I times J is K. This multiplication is called non-commutative. I times J is not J times I, the order matters. I times J is minus J times I, and I times J is K. J times K is I, and again non-commutative, anti-commutative. K times I is J, and K times I is minus I times K. So this is the definition of a quaternion. This is the number, by the way. Quaternion is a number. You can multiply 2 quaternions, you can add them, you can subtract them, and you can divide one quaternion by another. Suppose you had one quaternion Q1 and another quaternion Q2. There is a question is not how to divide Q1 by Q2. Okay. What is the chemical representation? It's very similar to complex numbers. Suppose you are given a vector in 3 dimensions. So that was the question, no? How to rotate a 3-dimensional vector in space? Is there a number system which can do it? So here is the vector, there are three directions, x, y, z. Here is a vector p, which has components 2, 3 and 5. X component is 2, y component is 3, z component is 5. P is the vector 2, 3, 5. Think of some other vector, any other vector in this space. So first let's write down P as the imaginary components of this quaternion. Okay? I know this I, J, K. I can always write a 3 vector in terms of the 3 imaginary components of the quaternion. The complex number was 2, here it is 3. Now I want to rotate it around another vector which has components A1, A2 and A3 in 3 dimensions. So I define a vector, I define an imaginary quaternion having this component A1, A2, A3, that's 2 tables. Okay? Now just like we did for a complex number, if I want to rotate P around Q by an angle of 30 degrees, first define this quaternion. This is a quaternion now. It has a real part, it has an imaginary part, 3 imaginary part given by this definition. The new vector Hamilton showed will be a vector P prime, which is Q times P times Q inverse. What is Q inverse? It is 1 over 3. Because you can divide it. The quaternion, the division will be 1, you can divide. So in this beautiful way, Hamilton, after a lot of hard work, showed that quaternions can explain rotation in 3 dimensions, just as complex numbers can explain rotation in 2 dimensions. Okay, this is the third division algebra. And let me skip this. So this will be useful for you sometime if you have learned what is given 2 vectors, you know what is scalar product and what is a cross product. They can be combined very nicely in the language of quaternions, but I don't think we need this. Okay. That brings us to the last of the 4 division algebras, the octonions. Quaternions have 4 components and octonions have 8 components, A0, A1, A2 all the way up to A7. These are 8 real numbers, and now there are 7 imaginary directions, E1, E2, E3, E4 up to E7. The square of each one of them is -1. For each one, that's like iota, that's the property. And any 2 imaginary directions are multiplied with each other anti-commute. The sign changes if you change the order of multiplication. Now to finally tell you how much is E2 times E3. This is in a quaternion, I times j was k, etc. Or E2 times E3. That is, there is a multiplication table shown in this figure known as the Farmer's range. You don't have to remember it right now, just know that there is a rule. So all the 7 directions, E1, E7, each one of them is denoted by a point in this figure. E1, E2, E3, E4, E5, E6 and E7. Suppose you want to know how much is E1 times E2, just follow the arrows. E1 times E2, so there are triples. E6, E1, E5 is a triple. E3, E2, E5 is a triple. So if you want to know E1 times E2, E1 times E2 is E4. Just follow this arrow. E1 times E2 is E4. E4 times E1 is E2. E6 times E1 is E5. And if you are going against the arrow, change the sign. E5 times E1 is E6 but is a change of sign. Magnify can be minus. So this is a multiplication table for octonions. We won't need it. We'll give you some idea. The multiplication is non-commutative. The order matters. It is also non-associative. Namely, if you have this is non-commutative. Non-associative is O1 into O2 O3 is not equal to, oh sorry, there's a typo here. This should be O1 O2. If you multiply O2 and O3 together and then multiply and then left with O1, it is not the same as if you first do O1 O2 and then O3. The quaternion multiplication is associative. Real number multiplication also associative. So the octonion multiplication is not associative. This is the last of the four number systems which are unit addition, division, multiplication, and subtraction is possible. Now we have this question. Why did I give you here? Our goal is to understand what is the gravitational field produced by elementary particles like electrons which obey the rules of quantum mechanics. They are not in one place, they are all over space, so they will define atoms of space-time matter. And we want to know what is the gravitational field of the electron. So now I'll explain to you why I talked of this division. What do the octonions have to do with elementary particles and what do they have to do with their gravity? Oh, this will bring us back to what we call physical space or space-time. Our three-dimensional space in which we live, like this room has three dimensions, length, breadth and height. These three dimensions are described by three real numbers. One real number along the x-axis, one along the y-axis, one along the z-axis. Real numbers or numbers in general describe physical space. A set of three real numbers describe our familiar three-dimensional space, and we all, these classical bodies which obey Newton's laws of motion, they live in three-dimensional real space. So now you can guess where I am going. The reason I have described these division algebras is because they have something to do with space and space-time. Okay. What do quaternions have to do with space? If you know some special relativity, Einstein showed that space and time are not distinct from each other. Together, they are part of what we call a four-dimensional space-time. So I have shown one spatial direction, the time direction. You can add two more. Space-time is four-dimensional, and I will not prove it to you. The geometry of space-time can be described using quaternions. So, three-dimensional physical space is described by three real numbers. Four-dimensional space-time is described by the quaternions. This is the space-time of special relativity. Classical objects which obey Newton's laws of motion or the laws of special relativity, they curve this space-time. So when we say gravity, as Einstein showed, is the curving of space-time, it is this space-time produced by these classical bodies which is curved. Okay? The space-time is described by quaternions, it's curved by stars and planets and galaxies. But notice, we have said nothing about elementary particles. Up until now, we have been used to thinking that elementary particles also live in this space-time, electrons and quarks. But when we do that, we still do not understand why charge is quantized, why mass is quantized. So remember, what did I say? That elementary particles obey the rules of quantum mechanics. They are spread out in space, and we want to know what kind of curving do they produce in space. One thing which is true is that the curving of this four-dimensional space described by quaternions is the curving as produced by large objects like planets and stars. Electrons cannot produce that kind of curving because they are all over the place. I do not know how to distinguish an electron from the space-time, or to make it more intuitive and precise. What we can note is that something which is spread around in space and in space-time will not produce curvature the same way as objects like stars and planets do, which are not spread out in space. That takes us now in the end to octonions. Octonions define an 8-dimensional space, just as quaternions describe 4-dimensional space-time. Octonions define a physical space which has 8 dimensions, labeled by the 8 directions of an octonion. I will now just give you the final result. There are very good reasons to believe that our fundamental universe is not 3 or 4 dimensional. It has 8 dimensions given by these 8 directions of the octonion. So you would say we see only 3. Where are the others? The others are very, very thin. They are so thin that we cannot detect them unless we do careful experiments. And if we ask this question, what is the gravitational field of elementary particles like electrons or quarks? The answer is that they curve this particular space-time which is described by the octonions. Large objects like stars and planets produce the curving of 4-dimensional space-time, but the 4-dimensional space-time we live in is only an approximate version of this 8-dimensional space-time, in which 4 of the dimensions are very thin, but they are needed nonetheless if you want to find out the gravitational effect of elementary particles which obey quantum mechanics. So elementary particles, which I call the atoms of space-time matter, are entities which live in this octonionic space. So what is an electron space-time matter? It is the electron plus the curving of this octonion space. It turns out that all the forces that we know, gravity, strong, weak, electromagnetic, together amount to the curving of this octonion space. Gravity is the curving of 4-dimensional space-time. All the 4 forces together are the curving of this 8-dimensional space-time, and elementary particles live in this 8-dimensional space. But that is not all. The most beautiful thing comes out now. In such a space-time which is octonionic, electric charge, it can be shown, can only take these values: 0, 1/3, 2/3, 1. And if you have heard of the fine structure constant, this famous number, you can prove that in the space of octonions, the fine structure constant actually takes only this particular value and no other. So we had started out wanting to explain What is the gravitational field produced by quantum mechanical particles? We found that their field is the field which curves the space of Octonion, and moreover, only these particular values of electric charge are allowed. So we understand charge quantization, and beautifully we also understand mass ratios. The numbers that I showed you, the mass ratios that I showed you, which were very strange numbers, actually can be proved that when elementary particles are described using the Octonions space, those numbers you can verify are given by these very simple fractions. The square root of the thing, the square root of the mass ratio. If we set the down quark as 1, all of the others are obtaining those numbers, crazy numbers that I showed you, are actually these simple fractions. This can be proved. So let us compare theory and experiment. So take the mass of the muon, 207 times the electron mass. Take the square root of the mass ratio. The observation is this value, around 14.3. Here it is 14.1, very close. Here, tau electron to electron 58, 58. 21 to 26, 23. 248 to 310, this is the experimental range, 289. 4.2 to 4.8, 4.16. 28, 30, 20. So actually we could, because we understand now that elementary particles produce the curving of the Octonion space, the Octonion space allows only specific values of electric charge and mass, and those agree with what we see in experiment. So we are to understand the nature of elementary particles by trying to understand their gravity. So what is quantum gravity? Quantum gravity is the fact that elementary particles curve the Octonionic space. That is quantum gravity. And it also turns out that in this Octonion space, only 4 different kinds of forces are allowed, which amount to curving along these different 8 directions. Okay? So the 4 known forces of nature are the only ones allowed in Octonion space, and we now have a candidate theory for the unification of forces. If you describe elementary particles on Octonion space and forces as the curving of this Octonion space, we actually arrive at a unified theory of the 4 kind of forces which Einstein dreamed. So here is my last slide. The law of gravity for large bodies is the one given due to Newton and Einstein. But elementary particles behave very differently from large bodies. They behave like waves. So their gravitational field cannot be described by Newton and Einstein's laws. To describe their gravitational field, we need the numbers known as octonions. And atoms of space-time matter are these elementary particles along with the curving of space-time matter. The universe that we live in is an approximate emergent phenomenon starting from the octonion. Our universe is also real, it's there, we live in it. But that is just an approximate description of a more exact description which is given not by real numbers but by octonions. And when we do that, we understand why the electric charge is quantized, why mass is quantized in those particular ratios, why there are only 4 kinds of forces. So the octonions really help us understand the various kinds of forces and properties of elementary particles. So I will stop here, and if you have any questions, I will be very happy to answer them.
Hello, sir.
Yes, please. Yes.
I am first. I am asking about the space-time curvatures for the elementary particle because, as we know, there is a certain probability of finding the elementary particle in space-time. So, on the basis of that, there is somewhere probability is maximum to finding the particle and somewhere approximately zero. So on the basis of that descriptions, we can define the space-time as curve like that.
Yes, so that's a very good point. Uh, what you know that the Octonion space is non-concentric space-time matter theory, and when you know right. So because of that, we can talk of the very nature of the elementary particle on an octonionic space. And just as you correctly said, you can define a probability distribution for elementary particles on this space of octonion. There is one more question somebody asked in the chat, is it? Let me see the question in the chat. Is Octonion space partition into 4D space? Almost correct. Almost correct. The more correct answer is that an Octonion space is equivalent to 10-dimensional space-time. 8 Octonion dimensions is equal to 10 ordinary Minkowski space-time dimensions. So then it is 4 plus 6. But no need to go into that complication. The answer is simply correct. It is partitioned into two different space-time. One which is our familiar space-time in which large bodies live, and the elementary particles, not that elementary particles are in the other half. They are all over. Elementary particles take all the 8 dimensions, but when lot of elementary particles get together to form large objects like chairs, tables, flying stars, the large object stays confined to 4 dimensions and has very little penetration in the extra dimension. So one question is, could we use hyperbolic quaternions to apply them to space-time method? I don't know what is this. What is a hyperbolic quaternion? So my ignorance. Maybe if you can tell me what is a hyperbolic quaternion.
चल रहा
I
सही
know complex quaternions.
हाँ ज्वाइन कर रखा सबने
You said that the four fundamental forces can be modeled as curvature in a 8D space-time method. Just how gravity is the Tejinder for 140 years. Space-time. But where does the bosons fit into? Very beautiful question. Excellent. Then I come to the next question. So boson, yes, because I wanted to use the top symbol, I did not bring in boson, but your question is very valid. Bosons are also described in terms of Octonions model. This Octonion space has elementary particles which are called quaternions. The Octonion space itself has elementary particles called bosons. In fact, when I talk of an atom of space-time matter, it has a fermionic part and a bosonic part. And the theory fits so beautifully that the known bosons of the particle physics theory experiment arise data we have of quantum gravity? And again, excellent question. The cleanest prediction is that we have so far seen only three kinds of neutrinos, which are known as left-handed neutrinos. The prediction is that there are three more kinds of neutrinos, the so-called sterile right-handed neutrinos. This is the cleanest prediction. Experimentalists must find three so-called sterile neutrinos which interact only by gravity. The neutrinos that we know of interact by the weak force and gravity. The sterile neutrinos will experience only gravity, and the Octonian theory predicts that they must exist. If they are shown to not exist, this theory will be proved wrong. Another prediction is something known as the dark photon. Photons are light. Light is photons. Electromagnetic radiation is photons. Similarly, there is in gravity, apart from what we already know about gravity, there is another bosonic particle newly predicted, which has spin 1 like the photon. It is long range, but it does not experience the electromagnetic, but it experiences only gravity. Just like the sterile neutrinos, the dark photon also experiences only gravity, and that should also exist. And the other important prediction is there is no dark matter particle. People are looking for dark matter particles. They have not been found. In this theory, instead of dark matter particles, there is a modification of the law of gravity on the scale of galaxies. So, if you have heard of modified Newtonian dynamics, the Octonian theory is related to that. There will be no dark matter, there will be a modification of Newton's law of gravitation on large. Are dark photons represent? Yes, yes, very good. Dark photons are predicted. Dark energy is dark photons. Correct. Another question is there any experimental method going to demonstrate or deny the existence of gravity? Very good, yes. Unfortunately, I don't know the answer. In this theory, there are no gravitons. Graviton is a spin to quantum of gravitation. Instead, in this theory, the fundamental particles of gravity are spin 1, like the other photons. If the graviton exists, it is not fundamental, it is a composite. But unfortunately, I do not have an understanding of showing that gravitons do not exist. It's a very good question. I don't know the answer. Excellent questions. I am very pleased you have asked very good questions. Does MON an alternative? No, not alternative to quantum gravity. Let me put it like this. We believe so far that the theory of gravitation is Newton's law of gravitation generalized to Einstein's theory of general relativity for relativistic systems. I am saying the Octonionic theory of graviton is more general than Einstein gravity and Newtonian gravity. In the solar system and near compact objects like stars and black holes, the Octonionic gravity theory reduces to Newtonian gravity or general gravity. On the scale of galaxies, where the rotation curves are flat, Octonionic theory reduces to MON. And on the cosmological scale, reduces to something known as relativistic MON, and the role of dark energy being played by these dark photons. So MON is not an alternative to quantum gravity. MON is a limiting case of this in my work more generally. But independent of Octonions, MON was proposed to modify Newton's law of gravitation and explain of space-time, but not of 4D space-time, but of the 8D Octonionic space-time. And gravity is the curving of 4D space-time. We didn't realize that there are these other dimensions. Of course, we still don't know. This is the theory, it has to be tested. The important, from my point of view, the very important signature that this theory could be correct is because it is able to explain quantization of charge and mass. No other theory has explained mass quantization or derived the value of the fine structure constant 1 by 137. So that is why I take this Octonions very seriously. Next question, is the Octonionic theory something like string theory and M theory or something? Very good question. Excellent question. It really is string theory, but in a much improved version. What has changed? We are defining particles using octonions. String theory did not do that. This is the most important change from string theory. There are a few other changes also. But yes, it really is string. I did not start to make string theory or improve string theory. I was mainly looking for answering this question: how do elementary particles curve space-time? That is how I came to the Octonions, and I realized that the physics of this Octonionic theory is essentially the same as the string theory. The gravity is the effect of curvature of space-time in space-time made of empty vacuum. And what is curving in terms of continuous spaces? Continuous space-time is an approximation. The Octonionic space is in a sense a discrete space-time, but if you don't look at it very microscopically, you get the impression of a continuum. In this theory, the continuum space-time is an approximation to the Octonion space. Octonion is like in mathematical, it's a number system. Yes, we realize that all these numbers are also important. Octonions were first discovered the same year that Hamilton discovered quaternions. His friend discovered, another mathematician, Irish mathematician, discovered octonions. That was 1843. Since then, many physicists and mathematicians have actually noticed the beauty of octonions and talked about their possible importance for particles. A lot of people have noticed that elementary particles and octonions seem to have a lot of connection with each other, and now that is coming to this, what I did not tell you whose all work I have done. This is the work of a lot of people showing that nature and elementary particles can be in space-time can be described in terms of octonions to get a unified theory. It's the work of many people. I have contributed to it. It's also the work of a lot of other people. If is vast space-time made of any matter like dark matter that interacts with normal matter through gravity? And there's no dark matter in my work. There are only sterile neutrinos and there is MOND. No dark matter. I hope I did not miss out any of the questions from the chat. So, what are the current research in the... Yes. Okay. This is the very difficult difficult and tricky question. There are many different approaches to unifying quantum mechanics and gravitation. There is string theory, there is group quantum gravity, there is something called asymptotic quantum gravity, and many other approaches. I will give you my personal viewpoint. I'm not satisfied with these approaches because they take quantum mechanics as given. They believe that quantum theory can be applied to gravity to make quantum theory. I disagree. My understanding is that quantum mechanics cannot be applied to gravity, and gravity cannot be quantized in the sense they are trying. Gravity and quantum theory both are emergent phenomena. So in the Octonionic theory, we are not quantizing gravity. We are saying that fermions and these elementary particles curve the octonionic space. This is very different from quantizing classical gravity. I'm saying from the curvature of octonionic space, both gravity and quantum theory are immersed. So your question is very good. What are the current research in the field of quantum gravity? So I tried to focus on my work. I did not the approach that me and my other like-minded people are following. And our claim is that we are able to explain things. We are able to explain charge quantization. We are able to explain mass quantization. We are able to derive the value of the fine structure constant 15137. Because we make predictions, in my opinion, we have an advantage over these other approaches which so far have not explained anything real. If you think I'm missing something, please put it in the chat box. So my personal view is that to try to quantize general relativity is a wrong thing. Instead, we have to find out in which way is space-time made more general by the presence of fermions like quarks and leptons, electrons and neutrons. For this specific network imaginary diagram, 1 second. Roughly. Yes, roughly yes. There's 4-dimensional real space-time, and there are the internal directions along with the standard model forces lie. Yes, roughly yes. So coming back to Archana's question, there is a lot of disagreement we can see right now. Most people are still continuing along the path of string theory, group quantum theory. Not the correct path on which to go. Gravitation and quantum theory are emergent phenomena coming from an underlying theory, which possibly is what I call this Octonionic theory of unification. And yes, and another important point to make, people are used to thinking that the unification of gravity with the standard model will have another forces will happen at very high energies, the Planck energy state. So I'm making a blog which you can find on my website with a link, where I explain that the unification of gravity and the other forces is needed at all energies. It is needed even in this room right now, not just at very high energies. Why? Because of this question I asked, what is the, okay, let me put down the link to the blog here. This is the link. Right. So the question was, why is the unification of gravity and other forces important even at low energies? Because I asked this question, in what way do fermions curve space-time? They cannot curve it like in general relativity, and we need some new kind of description of space-time to ask how fermions curve space-time, and that space-time is the octonions. So, and this is needed at all energies. To put it in a different way, if you have some quantum physics background, fermions do not live in a four-dimensional Minkowski space. Fermions live in an eight-dimensional spinor space-time, the Octonion space, which is like the square root of Fermion layer of Minkowski space-time. To arrive at the Dirac equation, Dirac took the square root of the Klein-Gardner equation, and he went from vectors to statements. When we arrive at fermions by taking the square root of the Klein-Gordon equation, at the same time, we must take the square root of Minkowski space-time to come at a spinning space-time if we want to understand which is the space-time in which fermions live. Fermions do not live in Minkowski space-time. That is a deception. Fermions live in the square root of Minkowski space-time, which is a spinor space-time. And when we do that, lo and behold, the standard model reveals itself. Why is charge quantized? Why is mass quantized this way? Why are there four different kind of forces? Why there are three fermion generations? All these questions get answered if you all these
है
questions get
भूमिका भूमिका
answered if you
रीड कर दिया ना, समझ
discuss
में नहीं आ रहा है।
fermions on the
हाँ तो वो तो है ही
Octonion
ना।
space. And
तो
this
कौन
is
है और
needed at all
सुप्रिया
energies.
ने लेक्चर अटेंड किया था, क्वेश्चन सेशन चल रहा है, जिसको डाउट है तो तब उसने
मैं पूछ रही अब है कोई क्लास का या
क्लास
नहीं?
का
बस ये बात पूछ रही
low
मैं।
energies at which we are currently doing experiments at the edge. This, I am certain, is correct. It is a change in thinking, and it is quite obvious in hindsight. We have not been dealing with the gravity of fermions in a sufficiently accurate way. I hope you get the picture. Fermions live on a spinor space-time, not in Minkowski space-time. Hey, what is the physical significance of a spinor? Yes, this statement about fermions is from recent. Yes, that is true. You also find it in the blog. I put everything together. What's the question? What is the physical significance of a spinor space or square? Very good, excellent, beautiful. So you see, fermions like electrons are described by spin, not by vector. They're very clear. Vectors and spinors have very different properties. A spinor is like the square root of a vector. Same way, the spinor space-time, or is, as we said, the square root of Minkowski space-time, it is the space-time in which fermions actually live. If we took the square of the spinor space-time, we will get Minkowski. Space-time is fundamentally not a four-dimensional space-time curved by gravity. It is fundamentally a spinor space-time. So the answer to the question, what is the physical significance of a spinor space? Space is spinorial. Space is not Minkowski. Minkowski space-time is an approximation, just like the Klein-Gordon equation is an approximation by squaring the Dirac equation. This is a new. See, Penrose talks of crystal space. That is spinor space-time. Penrose knows that fundamentally space-time is spinorial. But what he did not address is how is that related to particle physics. In fact, Kendall's been asking this question recently in his talks that he suspects that there is a connection between crystals, octonions, and particle physics. So, I have written to him, he was looking at my work. We have now actually found out the relation between octonions and particle physics. How to relate this to crystals is still work that remains to be done. So the answer to your question is very good. Physical significance of spinor spacetime is spacetime is spinor. Okay, at high energy we have TeV can easily take an SU3 to SU2 and even 3 color to 2 color and silver. You may be right, not in my theory. At around the TeV scale, unification is taking place in my theory. The left-handed standard model and right-handed gravity are unifying somewhere between 100 GeV and TeV. So the left-right theory, which has broken symmetry in total universe, will actually get unified somewhere around the TeV. Is the observable universe three-dimensional? It's a good question, a very good question. The observable universe spatial part, really 7 octonion dimensions or 9 spatial dimensions in this case. 1 time 9 spatial classical bodies like stars and galaxies are living in a 3-dimensional universe. That is why it appears 3 dimensional. It's like suppose you think of a disk. Think of a disk in which the thickness is much smaller than the horizontal radius. You will think that this is just a plane. Unless you look very carefully, you won't realize that the disk has a thickness. So the additional 6 spatial dimensions are very thin. That's why the universe appears 3-dimensional. But if we did not have those extra dimensions, in this theory, we would not be able to describe unification of gravity with the other forces. So we need those. In fact, I'm saying quantum particles live in 9 dimensions. Only classical objects live in 3 dimensions. Their penetration depth in the extra dimension is extremely. Whereas the quantum system penetrates the extra dimensions more than classical. Okay, yeah, thank you. Is it possible to share the slides of the talk? Okay, I will email it to the, or you please email me, I'll send you the slides. I'll also email them to the organizers. I don't know if they are recorded the talk. Is it all recorded? Okay, please find some way of sharing it with the people who are can note the talk. If you put it on YouTube or something, I will share the link on Facebook so that everyone can access it. Right. So, okay, so I will also, if you email me, will send me the slides of myself. And one Okay, thank you very much. Yes, thank you, thank you. But the one question is, what is your opinion on experiment where the electron divided into two charging particles, carrying charge and mass relations? I don't know this. Please also solve. I don't know this experiment. If you could remind me again, I will. Okay, thanks so much. I'm so pleased with your questions. Very, very happy to talk to all of you because these questions were really superb. So I want to convey this that we are moving in a new direction in unification of quantum gravity. It is in some sense because these ideas are very different from the previous ideas. There is a clash of ideas, when new ideas come, the old school thought needs to be thought, there will be a tendency to disagree. So I request you to think for yourself and ask which one looks more reasonable to you. I'm not saying you accept my thinking and not the old school of thought, but I have personally felt that almost 100 years we are trying to quantize gravity and unify all the forces. It has not succeeded. Even string theory is not successful so far in unifying all the forces. So we want to ask why has that not worked? And I hope I try to give you a new picture uh, by asking different questions. So we don't quantize gravity. Octonions theory predicted fourth generation. No fourth generation. Fourth generation not allowed. Three generations only. Left-handed neutrinos and right-handed neutrinos are three generations counted for. Fourth generation is to rule out this theory. If you have ever found out a fourth generation, the Octonic theory will be wrong. Okay. Can we log out now? I'm not in a hurry. If you have any questions, I think we are done. Otherwise, we are saying we can. Thank you so much. Thank you all for the pleasure. So please put this talk on YouTube and send me the link. I'll share it on my Facebook. So and if you don't find the link, just email me. And if you want the slides of the talk, just email me. I'll send you. Okay. Thank you. Bye bye. Yeah, more talks. Yes, tomorrow if you want, you can come. 3 o'clock, and it is announced on my Facebook page. And if you like to hear more about this, I will have to talk about it sometime. You can arrange again. So bye. Bye bye.